I'm going to be talking about surface tension and where we can find it in nature. So first I'll discuss where surface tension comes from and the physics behind it, and then I'll go through some examples of where we can see the effects of surface tension in nature, such as water striders, which I've managed to find on the lake. I couldn't get any good pictures of them, so I'll just be using pictures I found on the internet. And finally, I'll go through some of the equations that govern surface tension. Okay, so here we have a picture of a paperclip floating on water, and Archimedes here is a little puzzled because he says that his principle has the buoyant force here equaling the weight of the displaced fluid, which is going to be less than the weight of the object because the water has lower density than the paperclip. So obviously there must be some other force in action here, and that's surface tension. So if we look at the molecules inside a fluid, there will be intermolecular forces, and they'll be attractive, which is what keeps the fluid in one blob. And if we look at a particle here on the interior of the fluid, it'll have particles all around it, and it'll be attracted to all of them, which will roughly cancel out. So these forces, for example, water is fairly polar and has hydrogen bonding, which is just because the molecules have a dipole moment and they'll align to attract towards each other. But if we look at a molecule on the surface, it will be attracted to molecules inside, but not so much on the outside. And this is assuming that the cohesive forces, which are the forces between the molecules in the fluid, are stronger than the adhesive forces, so forces between the surface molecules and the molecules of whatever's outside here. In our case, air, I guess. So there's another interpretation of surface energy. This is the force interpretation. You can also think of it as minimizing the surface energy. So we can think of these outer molecules having a higher potential than these inner ones, and we want to minimize the total surface energy. So here, if we look at the dimensions of surface tension, that kind of makes it more clear, these two interpretations. On one side, we can think of surface tension as the force per unit length that an object experiences when we dip it in water. So if we place an object in water, there will be a contact line on the object, a one-dimensional line going around it, and at each point, we'll get a force per unit length equal to the surface tension, and we can integrate around this to get the total force. Or we can think of it as the total the energy per unit length, and then if we integrate it around the whole surface, which is two-dimensional, then we can get the surface energy. So just some sample surface tensions, just so you know about the order of magnitude of the forces in play. Water is fairly typical. It has a surface tension of 0.07 newtons per meter. And mercury has a much higher surface tension, which leads it to have these tighter balls. So you can actually make a little ball of mercury and roll it around. So it's about an order of magnitude stronger. Okay, so now I'm going to discuss some of the ways in which surface tension comes up in nature. So here we have a nice picture of a water strider. Water striders are more dense than water, but they're able to float on top of the water, and actually they use their middle legs to propel themselves by sort of using them as oars. So if we look at how these forces scale with size, if we assume the water bugs scale isometrically, then the mass of the bugs and their weight will scale as length cubed, and the surface tension will scale as length because it will be the surface tension integrated around that contact line. So just to see the contact line, the legs are fairly skinny, but you'll have a line on either side where the two-dimensional interface intersects the leg. So we can see that for any density, we can find a small enough length where it'll float, as long as this length doesn't get too small where we get into atomic scales or molecular scales. Okay, so another interesting way in which surface tension comes up in nature is these beetle larvae. So this is a beetle larva, and what it does is it actually bends itself so that these two angles here are different, and then it can create a net horizontal force from the surface tension and actually propel itself through the water using only surface tension. This motivated the creation of some little robot boats with no moving parts. They just have a little probe which emits an electrical pulse and lowers the surface tension, and it can move in the water. You can also take a small card or something and put some soap on one end, and the soap will dissolve in the water and lower the surface tension, and then it will propel forward. Okay, so a final application of surface tension. If we have multiple floating particles on an interface, they'll experience a force. If we have similar particles, it will be an attractive force. So here we have these Cheerios, or I guess Fruit Loops, and they're all attracted towards each other. This is why we get this clumping of our breakfast cereal in the morning. But then here we have these wax-coated, I guess, push pins, which have different wetting properties. So they're attracted to each other, but they're repelled by the Cheerios. Okay, so we're going to look at some of the math in these forces. If we have spheres, the force decays roughly exponentially with distance. It's not actually exponential. It's closer to a modified Bessel function, but with large distance, it's about exponential. But the decay length is what's important here, and that's going to be this parameter, which depends only on the liquid and the gas. So this doesn't depend at all on the properties of the spheres. So here, sigma is surface tension. This density is, okay, so it's the difference in density between the fluid and the air, but the air has negligible density compared, and g is just the gravity. Here, this beta is just a proportionality constant that will depend on all the material parameters. So how would we derive such a thing like this? Well, first we need to know what this shape looks like, and then we'll figure out the surface tension forces and do a vertical force balance. It's rather complicated. We're not going to do the whole thing, but let's just look at how the interface is shaped. So the Young-Laplace equation, which is this thing, I'll explain in a minute, it's derived by balancing the forces on the interface. So you look at a small section of interface, and you can look at if you make it small enough, then the mass will become negligible. And so we'll only have pressure forces and the surface tension forces. So on a perfectly flat interface, the pressure difference will be 0, and that's boring. But when we get curved interfaces, okay, sorry. I should mention, if the pressure difference is 0, h here is the mean curvature, which, okay, these R1 and R2, you can think of them as the principal radii of the surface. So, yeah, so 1 over R1 is one of the principal curvatures, and 1 over R2 is the other one. So if we have no pressure difference, then we get just h equals 0, which is the minimal surface equation some of you may recognize. And that's what we have when we get like soap films. But when we do have a pressure, we need to balance it with an equal force from the surface tension. And so we get the Young-Laplace equation. You can also derive it from an energy standpoint, where you calculate the total surface energy and the total energy from the pressure. Okay, so let's do a simple calculation. If we assume a two-dimensional model or an infinite cylinder, whichever you prefer to think of, we can calculate, okay, let's just go back. So you can express the mean curvature as this divergence of the normal vector. So if we express z in terms of x, we can get the divergence of the normal vector with some math to be this. And let's just approximate it to have very small slopes. Then we just get f double dot. If here f is just z. Then for a fluid in gravity, the pressure will just have this form. So P naught is going to be the pressure here out at infinity, where the pressure of the water is equal to the pressure of the air. And so then we just get this equation, which has simple exponential solutions. The exponential solution that blows up we'll throw away because we want it to be flat at infinity. So this exponential with this capillary length LC, that's where we ended up with the exponential decay of the force. And in general, capillary attractions will have exponential decays. So in summary, surface tension is caused by the attractive intermolecular forces. We find it many places in nature, such as the water striders and the beetle larvae, and it also gives rise to attractive or repulsive forces between floating objects. Thank you. Any questions? Yeah.
So the F in the F double dot equation
is
that's just the equation of that gives Z for X, right?
Yeah. So I'm just setting Z equals f of x. Yeah.
Right.
So yeah, here it's like. Oh, and okay. I'm going to set Z equals 0 at infinity. Yeah. Any other questions? No?
Thanks.
Okay. Thanks.